not now, but later. I was just making the announcement that I saw that some people's names had been removed from the permanent roll. I assume, I'm not certain of this, is because they had not completed payment yet. So if you are planning to stay with the course and haven't finished paying, you might want to check on that and make sure, see if you can get back in the class, because they did remove names from the roll. So try to take care of that if you can. The other thing I was going to announce, when you saw my locator card, the syllabus, and I gave my office hours, it had been on there Friday, 7:45 to 11:45, which has always been all term. However, this term has been a bit weird because last Friday, for instance, I had a doctor's appointment. The Friday before that, I had an infusion. The Friday before that, I had professional meetings in Jasper, Alabama. The Friday before that, I think I actually was on campus, over there. Three Fridays before that, I had infusions all 3 Fridays. So I've only been on the Birmingham campus for office hours one time out of the last 7, or something like that. Almost 2 months worth. I've only been on campus one Friday. Day after tomorrow, knock on wood, as long as nothing else changes, I should be on the Birmingham campus over there in the B building, the academic building. Far end of that building, Dr. Pruitt's office. I'm in the copy room of his office, and that's B122. However, they've called a meeting. They love calling meetings on Friday, and we have to be in the ACAT building from 8:15 probably till, I'm guessing, 9:45 or 10 o'clock. They haven't put an end time on it. They seldom do, and they never make it when they do. But there is I will be there. So I'll only be in the office from 7:45 to 8:15, and then sometime after the meeting's over with until 11:45. I'll probably be there a little later, but that's when it was. Is it Kima? Okay. How do you pronounce it? Kima. Okay. I thought I was saying it right. All right. And just missing Jeremiah and Kamari, or Kamari, however you say it. Okay. Now, as I mentioned before, some names that I'm calling here are not showing up on my rolls anymore, because I assume that not all payment had been completed. So if you know of anyone who is in that boat, please get your that straightened out so you can continue in the class and get credit for it. I mean, you can continue here as far as you like, but I can't give you a grade if you're not on the roll. Okay, so I love having you here, but can't have that without it. Okay, let's move on. Oh, one other thing I think we need to talk about. I don't know why they canceled school on Monday. It was, I guess, a big enough threat, but I sat outside with the dog saying we should be in class right now, and so we lost 2 hours, and we have lots to cover and very little time. Do you want to try to make up those 2 hours? I can't do it on the front end, but I could stay an half hour later or hour later, a few days, and catch up that, or do y'all need to go right at 6? What's your feeling? Or just cover what we can and hope that's going to be enough? There's no requirement for us to make that up because, it's not, that was school called it off. I didn't, I didn't miss something. But if you want to, in order to get all the information you need for your program you're going into, if you want to try to make that up somehow, I'm willing to do it. So what was there was a comment, I interrupted. What's your feeling?
Yeah, we'll be okay. We'll just be
okay. So we'll go keep 4 to 6. I have a developmental math class. I put the same thing to them. I had that earlier today, put the same thing to them, and they decided let's meet a half hour earlier for about 3 days, and try to catch up a little bit there. So we can go either way. Doesn't bother me at all. All right, then let's quit talking and get back to business. Everybody here did get a copy of the test, right? Okay, anyone who did not? Okay. And, yes? Page 130, is that what you said? Okay. Okay, my hearing's bad, so I may have to ask you to repeat something. Page 130, and what?
Yeah, can you work out that example 3?
Example 3?
Yes.
Okay.
Because I'm confused when you're changing the weight, it's supposed to allow more of what it's supposed to do.
Okay.
So if you can work out example
Okay. So do you want me to do example 3 again? Is that what you're saying, or you have a question about it?
Yes.
I'll just do it. Okay. Where is my pen? Oh, there it is. Okay. Okay. This is page 130, example 3, sort of in the middle of the page. Let's see if there's something that's going to be a little... Okay, we'll do it here. Oh, yeah, I'm sorry. I got it all set up, but forgot to press the button. It says, find the 75 kilogram astronaut's weight on the moon. So, let me get my pen. Okay. What we have is 75.0 kilograms. What is that a measure of? Okay, hit it one more time.
Mass.
Mass. That's the mass of the astronaut. All right, look at him. Okay. That's the mass of the astronaut. Okay. And what is the weight on the moon, where G on the moon, as opposed to on the Earth, this is an acceleration due to gravity, is 1.63 meters per second squared. On the Earth, it's 9.8 meters per second squared. On the moon, because the moon has a smaller mass, less density, lots of things going on there, its acceleration due to gravity is about 1/6 of that on the Earth. Okay? So it's saying, what is his weight? What formula relates weight to mass? Because we're looking for weight, that's the unknown. Okay? Now, this book calls weight F sub W. Okay? Different books name it different things. Some books, little w, that's why I wrote that down just off the top of my head. Others call it the force due to gravity, F sub G. This one calls it the force due to weight, F sub W. What is the formula for weight? Anyone know?
Force equals mass times.
Mass times acceleration, with this being the acceleration of gravity on the moon, which is G sub M. Okay? So this will simply be the mass, 75.0 kilograms, times G on the moon is 1.63 meters per second squared. And you'll need a calculator, I think, for that one. I can't do that one in my head. Anyone got a calculator? Yeah, see someone pushing. It's going to be something about 120, huh? Second? Okay, 122.25. Is that what you said? Okay. And what units? Okay, a kilogram meter per second squared is a Newton. Now, they probably don't give that as the answer in the book. Why? Because they do significant digits. 3 significant digits there, 3 significant digits there. So you take the first 3 digits, look to the right, 2 less than 5, just round that to 122.25. Is that what they got? Good for them.
So we should always round off to whatever.
Say again?
So we were supposed to round off.
Yeah. Here's the deal. The input that you have here is your mass with 3 significant digits. Any zero following a decimal point is significant. Okay? This is obviously 3 significant digits. No more, no less. Okay? So when you do the calculations, even though your calculator will give you a bunch of digits, you only use the first 3. 122. Look to the right from that last one. If that was a 5 or more, you'd round up to 123. If it's less than 5, you round down to 122. Okay? Was that the issue? Yeah. Okay. And for the life of me, there it is. Yeah, I saw the answer. When I first looked, I didn't see what their final answer was. All right, good deal. Any other questions? Good question. Okay. Now, am I as picky about significant digits as the book is? Probably not. When you turn in things, if you don't have the right number of significant digits, but you're in the ballpark, then I'll probably just correct the number of digits but not take off any points. But it's a good practice to only give in the number of significant digits you should have. Okay? Any other questions? All right. We were on example 3 in chapter 8, which is on page 210, and wait, sorry, I'm going the wrong way. Trying to find this is such a terrible PowerPoint selection here. Okay. I guess that's the best we can do. Okay. I don't even see that figure. I think I found it before. Yeah. That's on page 205. And there's not another figure in here until you hit page something like 213, 217, 216, something like that. So few and far between here. So here's example 3. The mass of a large steel wrecking ball is 2,000 kilograms. So the mass of this wrecking ball, so I'm going to put B for the ball, is 2,000 kilograms. Now, when they put the little bar over one of the zeros, okay, I said 0 following a decimal point usually will be significant. Zeros on the other side, on the front side of the decimal point, generally are not unless they're designated. Here's your decimal point right here. So that 0, if you just had 2,000, you assume 1 significant digit. If they put the bar over that one, that means 2 significant digits. Over that one, 3. If they put the bar there, that would have been 4. They put the bar here saying that's the significant digit. That means it's to the nearest 10 kilograms. That's your mass. Okay? 2,000. It's not, it could be 1,997. That would be to the nearest 10. Wait, yeah, no, I'm sorry. Yeah, and, or it could be 2,004. That would round to 2,000. But to the nearest 3 digits is 2,000. Nearest 10. Okay? What power is used to raise it to a height of 40 meters? So we're looking for power. That's the unknown here. Is used to raise it to a height of 40 meters. So let's see. I need to sort of draw this, I guess. I wish they had a picture I would copy. So here we have a wrecking ball, okay, hanging on to some crane or something here. Here's the ground down here. It's just supposed to be level ground, okay? and we want to, what power is used to raise that wrecking ball, which has this mass, 40 meters above the ground. So there's your height of the ball is 40 meters. And that's 40.0 meters to give it 3 significant digits, okay? If the work done the work is done in 20 seconds. So the height of the ball is 40.0 meters, and the time that it took to raise that is 20.0 seconds, which is a very precise time, okay? Now, to the nearest tenth of a second, okay? Now, how is power related to mass, height, and time? What is power? Last Wednesday was a long time ago. What is power? The rate of change of doing work. Okay? So it's work, rate meaning divided by time. Like the rate that you drove here is how many miles you drove divided by the time. How many hours or minutes it took you to get here. Okay, so this will be, so the power is work divided by time. Okay? Well, what is work? Help me. What is work? Remember my digging the patio out? The force times displacement. Exactly. So this is force times displacement over time. That's power. Well, what's force? What force are we dealing with lifting that ball 40 meters into the air? The 40 meters, by the way, is your displacement. So this could be your D. Okay? But what force was required to lift it 40 meters into the air? I stand on the scales and measure my weight. So we need to do weight. We just had that one on the board, didn't we? Right? F sub W, what was that? Mass times the acceleration due to gravity. Now, they didn't say whether we were on the moon or Mars or Mercury or where. So where we will assume we'll be. On Earth. Okay, good assumption, because that's where most wrecking balls are. Okay, so what would be your, we'll start with the force or the weight. What is your mass? 2,000 kilograms times your acceleration due to gravity. What's that on the Earth? 9.80, right? I can't remember. Meters per second squared. Some books use 80, some use 81. This one uses 80, I think. Yep. Okay, meters per second squared. That will give you the weight or force. So this will be the 2,000 kilograms times your 9.80 meters per second squared. Now times the distance. How far did you displace it? 40 meters. So that's your displacement, 40 meters up. And you're dividing that by 20 seconds, your time. Okay. Now, parts of this you can do fairly easily. For instance, 20 will go into 40 twice. Okay? And 2 times 2,000 would be 4,000 times 9.8. I'm just doing the math down here. 9.8. You could put the 0 there, but this will be 32. We'll have 2 zeros in front of it. I mean behind it. 32, 36, and 3, 39. 39,200 what? Watts. Okay, very good. Watts. That's what we measure power in the SI units. 39,200 watts. Okay? Or, since if you think that number is way too big of a number, and you want to use a smaller number but a bigger unit than watts, what could you do? Say again? I thought someone said it. What's the next bigger unit from watts? Kilowatts. And how many is a kilo? 1,000. So you move your decimal 3 places to the left, and you could write that as 39.2 kilowatts. The other reason that's a little more convenient, there's no ambiguity. Here, you can't tell if either of those zeros is significant. They're not. You don't have a line over them. But here, 39.2 kilowatts, it's obvious 3 significant digits. So that's another reason that would be a pretty good way to give an answer. That's a fair amount of power. But there's by the way, 2,000 kilograms. Anyone know approximately what that is? A kilogram is about, now these are not the same units, but on the surface of the earth, about equivalent to 2.2 pounds. No, did I say that backwards? No, that's right. No, yeah. Okay. No, 2.2 kilograms makes 1 pound. Yeah, 2.2 kilograms make 1 pound. What do we call 2,000 pounds? A ton. So if 1,000 kilograms, basically, 1,000 kilograms is what we call a metric ton, which is really close to being what our ton is. That's off a little bit, 200 pounds different, but not bad. So if it's 2,000 kilograms, that's 2 metric tons. So that would be close to a 2-ton ball. That's a big ball, okay? You're lifting 40 meters off the ground. That would be about like okay, I'm about 2 meters tall. Waist down is close to a meter, waist up is close to a meter. Okay? If I extend my hand upward, I come close to another half meter. So I would say that's another half meter up there. So it's about 3 meter room, high room. Okay? Fine. Okay? 3 meters high. Okay? A 40 meters off the ground would then be like 13-story building with this size room. That's up there, okay? About 13 stories high. So, yeah, that took a lot of power to get it up there. And you did it in 20 seconds. So that was moving along pretty well. Make sense? Okay. Let's move on to example 4. I think what I'll do is just clear what we've got here because there's no slide that has much more white space in this one, so we'll discuss them here. Here's example 4. A machine is designed to perform a given amount of work in a given amount of time. Oh, that's pretty specific, isn't it? A second machine does the same amount of work in half the time. Find the power of the second machine compared to the first. Okay? Now, the first thing they told us is the work by machine 1 is equal to the work by machine 2, right? And then they tell us that the second machine, we call it machine, or work 2, machine 2, does the same amount of work in half the time. So let's say the time 1 is 1, and time 2 for the second machine is 1/2, right? And it says find the power of the second machine compared to the first. We're looking at power for 2 compared to power for 1. What's the power for 1? What was our definition of power? Oh. Work divided by time. So that would just be W1 over T1, right? And what was, this will be 1/2 T1, okay? Half the time, okay? The power by machine 2 would be W1, because the work was the same, over T2, but T2 is 1/2 of T1, so instead of writing T2, we'll put 1/2 of T1, okay? Right? Because the work done was the same, but the time was 1/2 as much for the second one. So when you compare this to that, okay, these go out, okay, and you have 1 over 1/2. What is that? When you're dividing fractions, 1 divided by 1/2 is the same as 1 times. How do you divide fractions? Multiply by the reciprocal, 2 over 1. So the power for this one would be twice the power for that. Power 2 is equal to twice the power for 1. Okay? Now they didn't put the 1s and 2s there. They just did P for power, what I was calling machine 1. And the power for machine 2 would be 2 times the power for machine 1. Which, when you write this like this, here's what their equation turns out being. P is equal to 2P. Now that really doesn't make any sense, you know, unless you put the subscripts in there, okay? So P2 is equal to twice P1. That's what I was trying to say. And there, they just said P is equal to 2P. That doesn't make any sense, because P you would think would be the same variable. But the power is doubled when the time is halved. Remember my story of the bush, no, what did they call that? Bobcat. Did I tell you all that story? Digging out the patio? If he did it in a very small fraction of the time it took me to do the pretty close to the same amount of work, he had a lot more power. Okay, so same type deal. Let's go to example 3. Any questions on this? Good to ask questions while you're thinking of them. Got to find my eraser. A motor is capable of developing 10 kilowatts of power. 10.0 kilowatts. And they already told you that's your power. Okay? How large a mass, so we're looking for mass. That's your unknown here. How large a mass can it lift? 75 meters. So that's going to be your height or your distance of 75. I lost it. Yeah, 75.0 meters. I was thinking that's way up there, folks. Okay. 75 meters in that same time interval we used before of 20.0 seconds. It's going to be, okay, the previous one we had was 2,000 kilograms, and the power we came up with was 39 kilowatts. This is about a quarter of the power, so I would say it's going to be a lot smaller mass than what we did in example 3. But how do we figure this? What's your basic equation here? What's power? Work divided by time. But what is work? Force times the displacement divided by time. But what's a force? Force you're dealing with here is the excuse me, on the scales, the weight, and what's your weight? And that's F sub W. What is that? Formula for weight? Yep. Mass times acceleration due to gravity. So that would be M G D over T. There's your formula, right? Now, I think you probably had this back. We put it together. 8.2 started with just W over T, but then if you go back and figure out what W is, it's force times displacement from the earlier section. Go back even from that, and in the last chapter, force is mass times acceleration due to gravity. Okay? So, we know this. We know we're looking for this. This is what we're looking for. We know that, we know this, and we know that. So let's solve for the M. How do we do that? Let me write it all together. P is equal to mg d over t. Let's solve for M. Now, I know all of you love your fractions, right? That's your favorite, right? Everybody's favorite. I don't care for them that much. So I first want to get rid of my denominator. So what I'm going to do is multiply both sides by t. And that wipes out the denominator. But then I have to go back and we got to get rid of the GD. That should be a good word. So divide by G and divide by D, but you divide this by G and by D. So these go out here. That leaves you just the mass. That's what we're looking for, is the mass, is equal to power times time divided by acceleration due to gravity times distance. Now, you don't have to do it that way. You could have plugged in all your numbers to that first equation and then solve for the one thing you didn't know, mass. This way, you just takes less writing, solve literally by letter what you're looking for, and then plug in the numbers. What was your power? 10.0 kilowatts. Okay, that may be a problem. We'll hang on to that for a minute. Times time. What's your time? 20.0 seconds. Divided by your G. What's your G? Acceleration due to gravity, and what's that? 9.80, and that's meter per second squared, times your D. What was the distance you lifted it? 75.0 meters, and you're doing that in 20 seconds. That thing's going to be moving, folks. Okay, we have a problem here, Houston. Does anyone recognize what it is? Here we got kilogram over here, and we got meters and seconds over here. Now, what's a watt? Well, I'm sorry, let's back it off. What's a kilowatt? 1,000 watts. We need to get that in the watts. So that will be 10,000 watts. And what is a watt? It's a joule second, right? Remember that? A watt, I'm sorry, is a joule per second. I said it wrong. A joule per second, because it's energy divided by time. But a joule is a Newton meter, okay? And a Newton is a kilogram meter per second squared. So that's where the kilogram comes in. So we need this to be a kilogram meter per second squared, that's the Newton part, times meter, which is going to make that meter squared, then per second, so that's going to be per second cubed. So that's your unit for watts. You got to get it to watts, which is 10,000 watts makes 1 kilowatt, and multiply that by 20.0 seconds. Divide that by 9.80 meters per second squared. That's why we had to have that. And divide that also by 75.0 meters. Okay, if you pay attention to your units now, here's a meter times a meter. That makes a meter squared. Here's a second multiplied by a per second cubed. So that makes this a per second squared. But then you got a per second squared here and a per second squared there. So they go away. And that leaves us only with kilograms. Yay! Units are your friends. If you keep up with them, they'll let you know whether you're multiplying and dividing properly. In this case, it looks like we are. So the rest of it is just numbers. So 10,000 times 20 would be 200,000, right? Divided by 9.8 times 75. That's going to be something on the order of 740 something. Anyone got a calculator? 9.8 times 75. If you haven't noticed, most of this class is solving problems, okay? Good thing to have a calculator. You can just punch them all in at once if you wanted to. 10,000 times 20 divided by 9.8, then divide that by 75. Or you can do it like it says here, 20,000 divided by, and then put in parentheses 9.8 times 75, then hit equal. What do you get? You got an answer yet? Anybody? A little louder. Oh, I can't believe they did this. Oh, it continues on the next page. Good. Okay. Get an answer yet? Say again?
2,666.
That's not what they got. Let's 2,356. Is that what you said?
66.
Huh?
666.
Okay, it seems like it's way too big. Let's just take a look at this and see. It's 200,000, yeah. No, I'm sorry, I said it wrong. No, 200,000 divided by 9.8 times 75, which is something on the order of 700 and some. So let's just say around 750. It's not going to be that much. That would be, yeah, it's less than 1,000. Say again? 272. 1088 what? 435. And that would be seconds. No. Kilograms, right. I couldn't remember what we were going for. Kilograms. Okay. How many significant digits do we have here? 3, 3, 3. Our G was also 3. So we round to 3. We count over the first 3 digits. Look to the right. That's a 1. We don't round up. 272 kilograms. Okay? And that's what they got in the book too. Now they broke it down into smaller pieces. You could certainly do that as well. I went on and put them all together. You can do it in smaller pieces if you want to. It works either way. Okay? Now, and that kind of makes sense compared to our first problem, where we had a large steel wrecking ball of 2,000 kilograms, but we only raised it 40 meters. This was something we raised 75 meters, almost twice as high, in the same amount of time. And before we had close to 40 kilowatts. This was only a 10 kilowatt power motor, so we can only do a quarter of the work. So a quarter of your power, that would be a quarter of, and what they have was 2,000, that would be a quarter of that would be 500, and then because you went almost twice as high, take half of that, yep, around 250, 272, that makes sense. Okay? Is it making sense to you? Okay. All right. And then I think there's just one more example in this section. And this is example 6. A pump is needed to lift 1,500 liters of water per minute. So it's 1,500 liters per minute. Now, I don't know if I mentioned this to you. When we're talking about units, most of the time, if you have a unit with a capital letter, that means it was named after somebody. Newton, joule, watt, all named after people. Liter isn't named after anybody. Why would they use a capital L for liter? What does a small L look like? A watt. And then that would be confusing, okay? So they don't use little l. Now, some books will use a script L, with the loop in it, so it's obviously not a 1. I'm used to that one. This book uses capital L, so get used to them, whichever. Okay. And this is liters of water per minute, okay? I've got it, liters per minute. A distance of 45 meters, okay? So that sounds like to me you're lifting this water 45.0 meters, okay? That's a pretty powerful pump. What power in kilowatts must the pump be able to deliver? And by the way, they give you 1 liter of water has a mass of 1 kilogram. 1 liter this is a volume of 1 liter, has 1 kilogram of mass. Okay? Now, so if it's 1,500 liters, you have 1,500 kilograms. Now, I'm guessing that most of you are somewhat used to metric system. Is that right or wrong? Okay. When you're dealing with water particularly, water was what they used to measure mass. They had already determined in the metric system what a meter was. It's about 1/2 millionth of the distance from the equator to the North Pole through the, Paris, France, or something like that. And they had already determined what a meter was, okay? A little bit more than a yard. Well, then they took that meter down to centimeters, hundredths of a meter, and that was about the distance across your little fingernail. Now, they didn't use your little fingernail, I'm just giving that as an example. And 1 cubic centimeter, and back when my mom was a nurse, she used cc's for cubic centimeters. Nowadays, they mostly use cm cubed, okay? But she always talked about so many cc's, so many cc's. And it's not been that long since they quit using that, so you may have heard it too. Have you? Okay. Nowadays, especially for medical dosages, they don't use cc's or cubic centimeters. Cubic centimeters, you have to put that superscript 3, and people get confused with that. What do they use for measuring medical dosages now? Milliliters. And a milliliter was exactly a cubic centimeter. Exactly the same. So, if it's 1 gram per cubic centimeter density of water, that's 1 gram per milliliter. How many milliliters does it make to make a liter? 1,000. So 1,000 grams would be 1 kilogram. So that's where that comes from. 1 liter of water has a mass of 1 kilogram because of the density of water. Okay? So, the question here is what power in kilowatts must be able. So what we're looking for is power. That's the unknown here. Okay? So, we've already established this 1 liter per minute is going to be equivalent to 1,500 kilograms per minute, right? And that's going to be the mass rate. Now, you've got those per minutes in there, so you have to deal with that somehow, okay? So there's a mass per minute. How do we get that to power? Got to go through our whole rigmarole here. Mass is mass. You got to get it to force. What would force be? Okay, mass times acceleration of gravity. So your force rate, I'm going to call it, rate of force, is going to be 1,500 kilograms per minute times 9.80 meters per second squared. Okay? So that's going to give you newtons per minute, right? How high are you lifting that? 45 meters. So multiply that by 45.0 meters. That gives you your energy per minute, right? Kilogram, meter squared, per second squared, per minute. Energy per minute, joules per minute. What's the only thing wrong with that? A watt is a joule per second, right? So we could have done this at the very beginning. We can do it now just as well. This thing right here is going to be, I'll let you figure out the numbers, 1,500 kilograms per minute times 9.80 meters per second squared times 45.0 meters. Okay, that's going to be joules per minute, right? Whatever that turns out to, that's joules per minute. Kilogram meter per second squared is a newton meter is a joule. So that's joules per minute. So go on and punch those numbers in. 1,500 times 9.8 times 45. See what you get. See, 45 times 15 be close to 70, I think. Times 9.8 is going to be close to 10, so that's going to be about 700 or so joules per minute. I don't know. I'm guessing. What you get? Anyone got it yet? 661. Okay, say that again. 661,500. Okay, is it that big a number? That's 1,500 times 10 would be 15,000 times 45. That's 15,000, 150,000, yeah. Yep. That I could live with that. And that would be joules per minute. Okay, now I'm not absolutely certain of that. Okay, how do we get from 661, 500, right? Is that what you said? Joules per minute. And you need to convert that to blank, blank, blank joules per second. We've done that before, haven't we? How do you go from joules per minute to joules per second? You need a conversion factor there. Now, I don't sit around memorizing conversion factors, so I figure out what they are. My rule is always put the units in the place. This first blank here, right here, is for units. Now, I hate doing this because I want y'all to see it best, and if I just point to there, you just see a little dot moving around. This is for numbers, that's for units. But you see, the disadvantage of that, the people who are not here trying to listen at home, they can't see what I'm pointing at. So I'm always torn with, am I teaching you or teaching them? I'm supposed to be doing both, but I don't know. This is for numbers, that's for units. Always put the units in place. What units are we going to need? The joules are the same in both sides, okay? Both sides of the equal sign. Here we have minutes, there we have seconds. So we need minutes or second, one on top, one on the bottom. Where does it go? What goes where? Minutes on the top, seconds on the bottom. Now we match up the numbers with the units. How many minutes in a second or how many seconds in a minute? Say again? 60 seconds, 1 minute. Absolutely. Now the minutes cancel out and the seconds, oops, I don't mean for them to cancel out, that gives you joules per second. So take that 661, 500, divide it by 60, and what do you get? Say that again. 11025. Okay. Well, we only have 3 significant digits here, 3 significant digits there, 3 significant digits there, 3 significant digits everywhere. Now that 60 looks like only 2. But there are exactly 60.00000 seconds in a minute. So, yeah, you can make that anything you want. So we'll count over 3 digits here, look to the right. That's a 2. It's less than 5. So we'll just make this 11,000 joules per second, which would be what? Say again? What? What is a joule per second? What? A watt. Yes, a watt. What? Okay. That would be watt, but they asked for it in kilowatts, so how many kilowatts would that be? 11.0. Keep the 3 digits there. 11.0 kilowatts. Okay. How did the book do? Oh, look at that. They got it right, too. Okay. Now, I have a good memory. It's just real short. Did they only have odd answers in the back? I think so. So, problems here you can do any of the odds, either 1 or 3. I would say do either 1 or both of those. And then after that, any of the odds between 5 and 25. Okay? I would do some of each type. Say if you have several asking for time, do one of those. Several asking for power, do one of, at least one of those. Do several of those, and then go from there. So let's move to 8.3, which is energy. Now we've been talking about work, and what do we measure work in? What units? Say again? What do we measure work in? What units? Joules, okay. That's in the SI units, okay. In the U.S. customary, we use foot-pounds, okay. Now, energy, we'll find, we use exactly the same units. Energy is in many ways equivalent to work. Okay? And in your text, you'll see the things here. Energy is defined as the ability to do work. That's the first sentence in 8.3. Many forms of energy, such as mechanical, electrical, thermal, chemical, fluid, atomic, sound, acoustic energy, you just have tons of different kinds of energy. Sometimes hard to keep track of them. We're going to be dealing mostly with mechanical energy for right now. Mechanical energy is broken into two forms. There's kinetic energy, which is the energy of motion. Okay? So if I have this, say a baseball here, and I'm going to throw it to Chris, okay? If I throw it really hard, if I just lob it to you, does it take much effort for you to stop it?
No.
No. If I throw it really hard, you probably don't think it's much effort to stop it either because I'm not very strong. But it would take more effort to stop it. So the ball has the energy of motion. Now the mass is the same. What's changing is the velocity. So the kinetic energy is the energy of motion, and it's largely connected with velocity. Now there's another form of energy, and that's the energy of position. Okay? Now I'm going to take this book, and I'm going to hold it over Chris's foot. Okay? And I'm going to hold it over his foot here and drop it, and he'll yell a little bit. But if I dropped it from here, he would yell a lot more, because the book has more energy when it was up there than when it was down here. Why? Because I had to do work on the book to lift it, right? It's weight times the distance I lifted. That's the work I did. So every amount of work I put into it is adding more energy, so it would make a bigger bruise on his foot, okay? So that would be worth it, right? Okay. So, that's the energy of position. It wasn't, I moved it a little bit, but I moved it really slowly, constant speed. It really didn't matter. But that was the energy of position. Whereas I throw a baseball, it's the energy of motion that he's having to deal with. Okay. Now, there's several types of potential energy as well. One of these is called internal potential energy. That would be all the energies that make up the substance. For instance, say gasoline. I don't want to follow the whole pattern here, but where did gasoline get the energy it has? Don't you agree that if you light gasoline, you're going to produce heat? That's energy. Where did it get that energy? The sun. Now, how did it get it from the sun? Well, probably hundreds of thousands of years ago, when the earth was covered with plants, and those plants, little green leaves out there, are constantly photosynthesizing, taking carbon dioxide from the air, water from the roots, and forming carbohydrates, sugars, simple sugars, right? And then the plant takes those and stores them as more complex sugars, or possibly as fats or oils, okay? Pecans would be, largely fat, whatever the plant would be. Most of the seeds have a lot of fat in them, and protein, other things too. But over the years, that leaf mulch, the wood, the seeds, and everything else got packed and packed and packed and packed and packed, packed into the earth, and with great heat and pressure, that organic matter converted to either coal, which is kind of dirty, or petroleum, which is a little bit cleaner, or natural gas, that may be the cleanest of them all. So we were talking about gas. That's where the energy came from. The chemical energy that was a result of photosynthesis of the sun in those leaves, those little green tiny leaves out there, they are what gave gasoline many centuries later its energy. Okay? A compressed spring has potential energy because the spring itself, if you played with a spring before, right? If you stretch a spring, it's pulling back on you all the time, right? Or if you compress a spring, it's pushing out on you. So that's potential energy. Whatever you compress it, it's not moving anymore, but if you release it, it springs back. Or when you stretch it and release it, it springs forward. So it has potential energy. So all those are forms of potential energy. When I was holding the book over Chris's toe, what kind of energy did it have? That's called gravitational potential energy, because it was work I did against gravity that I had to do lifting the book. We're going to focus on gravitational potential energy for now. We may do some other, but we will do, we're going to focus on this now. And the formula for gravitational potential energy is, let me see if I can find, yeah. We're going to get closer to this one, okay? And this book uses capital E for energy, P for potential, and I don't see where they get the G here at all, so I like to call it E sub, well, actually what I like to call it is GPE, gravitational potential energy. That just makes more sense to me. They call it E sub P, but that's any kind of potential energy. So I'm going to put E sub GP, gravitational potential, okay? And that is the mass times the acceleration due to gravity, that's where the G comes from, times the height. And what does that look a lot like? What's mg? Which force? Standing on the scales? Weight. Mg was the force due to gravity. Weight, right? No, F sub W the book uses. Force due to weight, okay? Times height. That's the work I did lifting the book, right? mgh, mass of the book times acceleration due to gravity times the height I lifted it. And that was going to be damage to his foot, right? So that was going to add potential energy to that. So there's your gravitational potential energy, mgh. Okay? Where EP is potential energy, I like to call it gravitational potential energy. M is the mass, G is acceleration due to gravity, which is either 9.80 meters per second square or 32.2 feet per second squared. We haven't used that much, but it is that. And H is the height above the reference level. So anything you're talking about energy, especially potential energy, you always have to establish your reference level. Okay? Now what does that mean? Well, when I was going to drop the book on his foot was going to be the reference level. That's as low as it's going to go in that problem until he starts kicking me. Yeah, well, never mind. Okay, so that's the reference level. Now, if we were up on the second floor like they first put us, we could use the floor as a reference level. If we were going to lift something off the floor and drop it to the floor, that was going to be it. That was it. But if we went over to the window on the second floor and dropped it out of the window, then the ground would be the reference level. So you have to determine where is as low as it's going to go in this particular problem. That's your reference level. The ground out there and the floor in here are about the same height, so I could use that as the example here. Or I could have used the tabletop. If I held the book up here above the tabletop, that would be my reference level. Unless, as low as it could go, could be the floor, then that would be my reference level. But you decide the reference level ahead of time and stick with it throughout the problem. So that's called the zero reference level. Where is the zero level of your activity? Okay? Okay. Height above the reference level. Here they're back with the wrecking ball. Okay? This time they only have one with 200 gram mass. Is poised. This is example 1. So do you want me to leave that formula there? You think we might need it? Oh man, okay. Y'all are getting clever on me, okay. So let's just erase the GPE here. That's what I like to call it, but obviously the book doesn't like to call it that. So we will call it E sub P, but I'm going to put the G in it anyway, so you know it's gravitational potential. Okay, a wrecking ball of mass 200 kilograms. They already told us what that was. Mass of the ball is 200, and the third decimal, second zero is significant, so you got 3 significant digits. That's kilograms. There's a wrecking ball mass. Is poised 4 meters above a concrete platform. So let's just imagine the wrecking ball's up here. Here's a concrete platform, and this is your 4.00 meters. That's really precise. So that's your height. Okay? Whose top is 2 meters above the ground. Oh, here's a picture in the book. If you got your book, you see that picture. It's much better than mine. Okay? Here is the ground down here, so this is 2 meters, 2.00 meters. That's ugly. .00 meters above the ground. So that's about 6 feet above the ground, and then the wrecking ball is another 12 feet above that. That's approximate, okay? Now, with respect to the platform, this right here, if that's your zero reference, what is the potential energy of the ball? What's your formula for potential energy? I left it there, didn't I? Yeah, there it is. MGH. So, M is 200, with the second zero being kilogram, times G is 9.80, because we're using the metric units here, meters per second squared, times, if you're doing from the top of the platform, that would just be 4.00 meters. That's how high it is above that. So your potential energy, gravitational potential energy for that ball above the top of the platform is, that'd be 800 times 9.8, that's going to be 7,000 something another. Right? What you get? 7,800 what? 40. Okay. Boy, came out with the right number of significant digits too, and that would be what unit? What unit do we measure energy in? Joule, same as work. Joule. Now, if you think that's too big a number, and you want to use a smaller number but a bigger unit, what would that be? Say again? If you wanted to use a smaller number but a bigger unit, what would you use? 7.84 1,000 kilojoules. And the other advantage of that is it's obvious there you have 3 significant digits. Up here, you may wonder, is that zero significant or not? No, it's not, but you can't tell. Maybe I just forgot to put that over it. But so that would be 7,840 joules would be the potential energy with respect to the top of the platform. But the B part says, with respect to the ground, what is the potential energy of the ball? So the E, I'm going to put GP, okay, gravitational potential energy, with respect to ground. This was with respect to, I didn't even put it down, platform, okay. Only thing that changes here is your height changes, right? You still got a mass of 200 kilograms. You still got 9.80 meters per second square acceleration due to gravity. But now, how high are you from the ground? If the ground's your zero reference level. 6 meters, 6.00 meters. Okay? So that would be 1,200 times 9.8, which would be 11,000. Say again? 11,760. What units? Say again? Joules. Okay. Which would then be about, if you use a smaller number, bigger unit, $11.8 kilojoules. Why did I do that? 3 significant digits everywhere, folks. You can't get more significance out of the problem than you put in. So really, this one should have been 11,800 joules, but I'll let you get by with that because I was going around in a minute. And that's why they have 11,800, whereas your calculator told you 11,760. Count off 3 digits, look to the right, it's greater than 5, round that last one up. All right. So that was your gravitational potential energy. Guess what? G is in there, gravity in there every place, okay? And what goes with G? mg, that's your weight, okay? And then the other thing is height. And by the way, it's only vertical distance that matters with gravitational potential energy. The pin on the table right here has the same gravitational potential energy as there. There's no difference in height, okay? Good. I got my pen back. Jeremiah's here. So we have everyone here except Kamari or Kamari. Does anyone remember how to pronounce her name? Kamari. That's what I thought she said. Okay. I keep wanting to call it Kamari. Okay. Now, one thing I was mentioning earlier, some people's names, I don't remember whose now, have fallen off the roll, and I think it's because of payment. So, oh, you're over there taking care of it. You got back in then. You'll be able to see and hear everything once it gets loaded. Probably be sometime late tonight or tomorrow before this gets loaded, but you'll be able to catch up with where we were. So there's gravitational potential energy, mgh, where h is measured from your zero reference level. You have to determine that before, otherwise you don't know what your gravitational potential energy is in reference to. We just saw if it's on the platform or on the ground, it changes from 7.84 kilojoules to 11.8 kilojoules. Okay. Now, what was the other form of energy? Not energy of position, but the energy of motion. What was that called? Kinetic energy. If you remember back when we were mentioning friction, didn't we mention friction? We had static friction, and then we had kinetic friction. Anything that has to do with motion is kinetic. Any of you a kinesiology major or take any kinesiology courses? Okay, I thought maybe you had. Okay, that's dealing with motion, right? Okay, all kinds of motion. Okay, well, here we have kinetic energy. So let me clear the screen here. Whoops, hard to see down here. Okay. Kinetic energy, we call that E sub k. Now, we don't need any other initial with kinetic energy. I usually call it EK. The book calls it E sub. I usually call it KE, kinetic energy. The book calls it E sub k, energy kinetic. Why? I don't know. Okay, here's the formula for it. All that matters is this. It has a 1/2. We'll talk about that in a minute. mv squared. That's it. Kinetic energy. There's only one form of kinetic energy, and that's it. 1/2 mv squared. Now, where does the 1/2 come from? Most of physics comes from the branch of mathematics called calculus, because it's instantaneous stuff. And calculus, when you're dealing with that, you usually have this integration constant. And most of the time when your variable is squared, you're going to have something with 2 in the denominator in front of it. You'll see that over and over and over again. Now, sometimes the books will refer to it as average this or something like that, and you can refer to it that way, but where it really came from is calculus. Since this is not a calculus-based physics course, just have to believe me, the 1/2 is there, 1/2 mv squared. So, if I threw Chris the baseball, and at the same speed I threw him a bowling ball, which is he going to duck and try to have it hit Dana? I don't know, he wouldn't do that. Which would you rather catch?
I really catch the baseball.
Why is that? It has a lot less energy than the bowling ball going at the same speed, because the bowling ball's mass is so much bigger, right? Now, we already gave this one, baseball at 5 miles per hour as a baseball at 60 miles per hour. Rather catch the 5 miles per hour, because it doesn't hurt as much when you do, you know. And I can't imagine the people having to catch some of these professional baseball players that throw at 90 to 100 miles per hour. No. Sore hands, sore hands. Okay. So there is your kinetic energy. M is the mass of the moving object. V is the velocity of the moving object. Actually, that V is the speed of the moving object. Okay? You can call it velocity, but the direction really doesn't matter here. Okay. Now, they're giving an example related to something pretty similar to what we've got here in the book. A pile driver, which this is sort of representing here, shows the relationship between the energy of motion to useful work. The energy of the driver is the kinetic energy as it hits. When the driver strikes the pile, work is done on the pile, and it is forced into the ground. The depth that goes into the ground is determined by the force applied to it. Hey, what's that? Force times the distance? Didn't we have that earlier? Work! So the energy done, kinetic energy of that pile driver, big mass, really big mass, going at a pretty good rate of speed, that's going to give you the amount of work it's doing driving that pile into the ground, force times the displacement. So that sets us up for example 2. This is not far from this figure here. I take it you probably want me to leave that formula on the board. What we're going to do is set this equal to Fs, where F is the force and S is the distance that drives it into the ground. Okay. A pile driver with a mass of 10,000 kilograms. Okay. So the mass here is 10,000 kilograms. That's about 10 metric tons, which is a little bit more than 10 tons. That's a lot of mass, okay? Strikes a pile with a velocity of 10 meters per second. So that was supposed to be a V. It didn't look like a V, did it? Oops. Okay, let's try it again. Velocity of 10.0 meters per second. That's going along pretty good rate, Okay? Pretty high velocity. A, what is the kinetic energy of the driver as it strikes the POW? So what is K? E sub K. Okay? What is that? 1/2 mass, which is 10,000 kilograms. That's a big number. Times 10 meters per second. But what you do with that 10 meters a second? Square it. Whoa. This could get substantial, couldn't it? So that's one. Let me just take 1/2 of 10,000, make it 5,000, okay? So I don't have to mess around carrying that 1/2 around. So it'll be 5,000 times, I'm just dealing with numbers here. What's 10 squared? 100. And it'll be meter squared per second squared. So this, I'll put the units in. Kilogram meters squared per second squared. Okay? And that would be 500,000. What's a kilogram meter per second? Meter squared per second squared. Kilogram meter squared per second squared. What's that? Joule! Okay. Pulling teeth here. And if you wanted a smaller number but a bigger unit, that could be expressed as 500 kilojoules. And you could leave it just like that with that second zero, third digit being significant. Or if you wanted even a smaller number and a bigger unit, what would that be? Anyone know? That would be 0.500 there. You don't have to put a bar over it. Megajoules. Mega means a million. Kilo is 1,000, mega is a million. Just think about your computers and the bytes or the speeds and things like that. They used to talk about how many kilobytes computer memory it had. They really bragged on it. This is 10 kilobytes. Wow, that's the early PCs. Okay. And then they had disks that would carry megabytes. And then they have things that will hold gigabytes. And then they have ones that are terabytes. Okay. It just keeps getting bigger and bigger and bigger. Every one of those is another power of 3. Okay. So that's the kinetic energy as it strikes the POW. That's 500 kilojoules. That's what we said. Okay. Okay. Now, I'm losing my voice. The B part of the problem says, if the POW is driven 20 centimeters into the ground, what force is applied to the POW by the driver as it strikes the POW? Okay? So if that's your energy, this was, let's go back to 500 joules, I would say. 500,000 joules. Okay? And that's equal to your force that it strikes it with, and it's driving it, how far did it say? 20.0. So your S here is 20.0 centimeters. But wait, time out, folks. What's wrong with this picture? Joules and newtons and all those things depend on meters per second squared. The acceleration due to gravity, everything else, meters. Your speed was in meters per second, 10 meters per second. You don't want centimeters in the problem. So you need to convert that centimeter to meters. So we're going to do a times blank blank equal blank meters. Now you have to decide. The first blank there is for numbers We're not going to fiddle with numbers yet. Second blank for new units, always put the units in their place. So what unit goes where? Above or below the line? Between centimeters and meters? Centimeters go below the line, is that what you said? Okay, and meters goes above the line. Now we match numbers with the units. How many meters in a centimeter or how many centimeters in a meter? Second? 100 what? Which? 100 which? 100 centimeters is exactly 1 meter. You got it. Okay? So therefore we got to divide this number by 100, which means moving the decimal 2 places to the left. So that's 0.200 meters. You need those zeros in there for your significance. So this is what we're going to multiply by 0.200 meters. Okay? Yes? Oh, okay, just stretching. Okay. All right. Now, I want to ask you another dumb question. What was our definition of a joule? Does anyone remember? Especially in terms of meters. Something meters. A joule was remember what? Joule measures work, and work was something times something. Force times displacement, right? And displacement is measured in meters, and force is measured in mass is involved. Okay, pound in the U.S. customary, but what in the SI units? Good old Newton. Good old Sir Isaac Newton. So let's go back up here to our 500,000. That was joules, which are Newton meters, times, that's equal to, okay, the force, that's what we're looking for, times 0.200 meters. So how can we find the force? Second, divide both sides of the equation by 0.0200 meters. Okay, here it goes out. Now, notice here the meters go out. That's why I had you go there. So this is going to be force in newtons. Yes, that sounds like a good unit. And when we divide this, what I do is move the decimal 1 place here and 1 place there. Okay, and then do 2 into 5 will be 2, 5, 0, 0, 0, 0, 0, which is 2,500,000 newtons. 2.50 meganewtons. Okay, we usually don't use that term, but what did they get? Whoa here. Oh, okay. They left it as 2.50 times 10 to the 6. 10 to the 6 is mega. That's a million. So same answer. Okay. A lot of times with newtons you don't see the prefixes in front of them. I don't know why, but they just left it as 2.5 times 10 to the, 6 newtons. Okay. Oh, here's example 3. I was saying, looks like another example, but I didn't see the thing over there. So let's clear this. Let me just make sure we've not got a, I don't think so. Yeah. Actually, we've got more white space here. Let's work this one here. A 60.0 gram bullet is fired from a gun with 3,150 joules of kinetic energy. Find its velocity. So what we have is a 60 kilogram bullet. What is that a measure of? That's the mass of the bullet. Okay? Is fired from the gun with, and they told us the kinetic energy here, E sub k, is 3,150 joules of kinetic energy. Okay? Now, when they write it like that, and they don't put a bar over the zero, that zero is not significant. So that's 3 significant digits. The 60 is 3 significant digits. Okay? Now, the question is, find its velocity. Any formula come to mind? That's what we're looking for. Say again? Say again? Kinetic energy formula, how does that go? E sub k is equal to 1/2 mv squared. No changing it to forces here. Mass is exactly what we had. That's perfectly fine. Now the question is, do you want to solve this literally and then plug in the numbers, or you want to plug in the numbers here and solve for the thing that we're missing, velocity or speed? I don't care, really, too much. Which way you want to do it? Plug and chug or chug and plug? I don't care. Plug and chug? Okay. Huh? Chug and plug? Okay, so first solve for V and then plug in the numbers? Okay, we'll do that. How do you solve for V here? That's what we're wanting to solve for. It's the first thing you want to get rid of. How about that denominator? How do we get rid of it? Multiply both sides of the equation by 2, right? That wipes out the denominator there. So that gives us mv squared is equal to 2 e sub k. Okay? Now we're trying to solve for v, so what do we get rid of next? M, how do you get rid of it? Divide, because it's multiplied. Okay? Undo multiplication with division. So that gets rid of your m. But that gives me a v squared is equal to 2, I can't write, e sub k over m. I want v. So how do we undo a square? Square root. So v would be the square root of 2, I keep doing that, e sub k over m. Okay? Now, most of the time in mathematics, when you take the square root of both sides of an equation, you have to put a plus or minus in front of the square root sign. But guess what? We're dealing with kinetic energy. Do you think you ever have negative kinetic energy? No. So we don't have negative velocities either. We just have speed. Okay? So we don't do the plus or minus. So what we do here is now do the plug. That was our chug. Here's the plug. It's 2 times, and what was our kinetic energy? 3,150 joules divided by m, 60.0 kilograms. Well, I have a problem with this. Okay? Here's what I'm having a problem with. I need the basic units for joules. So that's 2 times 3,150. What is a joule, by the way? I already mentioned it one time. 60.0 0. Oh, it's grams, isn't it? Oh, good catch there. We've got to get that grams to, I thought that's an awfully big bullet. I call that a shell, not a bullet, okay, as you'd fire from a big gun on a ship or something. That is grams, you're right. But everything else is in joules, is in Newton meters, and a Newton is a kilogram meter per second squared. We need it in kilograms. So what had we better do to this? Good old conversion factors, and we need this to be kilograms. The first line there is for numbers. Don't mess with them yet. Always put the units in their place. What unit goes where? Kilograms on top, grams on the bottom. Now match the numbers with the unit. How many kilograms in a gram, or how many grams in a kilogram? Second? 1 kilogram equals 1,000 grams. Absolutely. A kilo means 1,000. Okay, so 1 kilogram is 1,000 grams. Okay. So this dividing by 1,000 is going to move this decimal 3 places to the left. So that will be 0.0600 kilograms. So that is 2 times 3,150. Now what? Okay, get me back to basic unit for joules. What is a joule? Okay, it's a kilogram meter squared per second squared. Because remember, a Newton is a kilogram meter per second squared. A Newton meter would then multiply another meter by it, so that gives us that. And then we're going to divide that by 0, and this, let me correct that. Okay. Our mass was 0.0600 kilograms. Okay, much smaller number there. 0.0600 kilograms. Okay, now notice your kilograms will cancel out, and that gives you the square root of a pretty good sized number divided by a really tiny number, which is going to be a really, really, really big number. That'll be the square root of 6,300 meters squared per second squared divided by 0.06000. Oops, 00. Okay. Now what I'm going to do this division is move this decimal 2 places to the left, move that one 2 places to the left. Okay. So that's going to give me the square root of, now 6 will go into 6 1 time, 6 will go into 3 0 times, 6 will go into 30 5 times, and then we've still got 1, 2, 3 more zeros after that. Okay? So I got the square root of 105,000, and these are meters squared per second squared. Okay? Someone with a calculator, punch that in and see what the square root of 105,000 is. So that's going to be about 300 and some odd. Second? 324? Okay. 324, and you take the square root of the units, meters per second. What a nice measure for a velocity, right? That's what we're looking for. Velocity or speed, about 324 meters per second. 324 meters per second. That's what the book had too. 3 significant digits. Okay? There's a little bit of verbiage here after that third example. They talk about spring potential energy, compressed or stretched spring containing potential energy. Robert Hooke was the guy who was responsible for that. You'll hear them talk maybe about Hooke's law. I don't think you'll need that in the DMS program, but if just the fact that you've had physics, you've now heard the term Robert Hooke's and Hooke's law. And there's also the spring constant is measured usually in Newton per meter. I guess you could have pounds per foot, but most of the time it's Newton per meter. Okay, problem set 8.3. I would do either 1 or 3 or both. And then, again, choose any of the odds 5 through 21. And do some of each type to make sure you have a good understanding of what's going on there. Sorry, I'm yawning, folks. My wife was in Denver for quite a while since last weekend, and she flew back last night, and the only flight she could get, the most convenient, was she got in after midnight last night. So I'm kind of, and I was at work at 7:45, so it's been a short night. Okay. Let's move on to, and actually I go back one. Here is where the figure that we saw there. Close to 10 pages since the last figure. And this was conservation of mechanical energy. Now, someone remind me what it was what was mechanical energy? It's the sum of two other energies. About the only two we've really talked much about. Yes, the sum of kinetic energy and potential energy. That's what mechanical energy is. Generally, kinetic energy is not conserved. Generally, potential energy is not conserved. But the sum of the two generally is conserved. Like if I was going to hold my book above Chris's foot again, okay? Now what I did, I gave work, oh goodness. I did work on the book by lifting the book, so I'm doing that. So now it has potential energy. If I were to drop it right before it hits the floor, what kind of energy does it have? Hint, it's moving. Kinetic energy. Okay? So it wasn't my potential energy that hurt his foot. It was the kinetic energy. That's not my fault. Oh, no, I'm just kidding. Okay? That was kinetic energy at the bottom. And guess what? The sum total of those was your mechanical energy. Up here, all the mechanical energy was potential. Right as it hit the floor, it's all kinetic. Okay? Because if you use the floor as your zero reference plate. So the sum of that is potential energy. Is mechanical energy. Anywhere in between, it has some potential and some kinetic. That sum is always constant. Okay? The sum of the two is always constant. We usually deal only with the endpoints, but anywhere in between, the sum of the kinetic and potential is mechanical, and that's usually constant, meaning the mechanical energy is always conserved. The sum of kinetic energy and potential energy in a system is constant if no resistive forces do work. So in other words, we're ignoring air resistance. We're ignoring any kinds of frictions and things like this. And the book falling through the air, it's not really going that fast, so the air resistance is pretty negligible. Especially if I drop it like this, so it's thing. Very little air resistance here. If I dropped it this way, maybe a little bit more, but still not very much because the velocity is so small. Okay? So here we're back to the pile driver, and this is where I should have been. I was using it before, but here's where it is now. I don't have anything behind there. Okay. Here is the crane lifting the pile driver, dropping it on the pile. Okay? Now, Your potential energy, when it's up here before you released it, is at a maximum. The kinetic energy is 0 because it's at rest right there. No velocity. So potential kinetic energy is 0. You're going to drop it a height of h. Now this thing has a certain mass, and we know what g is, and we know what h is, and what does the product of those three give us? The potential energy, gravitational potential energy. mgh, gravity. mg, weight, times height. Okay? Now, at any place along there, including the top, the kinetic energy is 1/2 mv squared. Okay? Up there it's 0 because it has 0 velocity. Now, if you're measuring your height from the top of the pile, which is what we're doing, that's your reference level. So that's the height where it's measured from. The kinetic energy here is going to be 1/2 mv squared, right before it hits. Here, your potential energy, this is Ek at the bottom. This is Ek at the top, okay? And the potential energy at the bottom, E sub P, I like to call it GP, here is 0 because that is your 0 reference level. The height there is 0, okay? So, if the sum of these two equals the sum of those two, that just means that's equal to that. So, let's set that equal to each other. 1/2 mv squared, this is v at the bottom, is equal to mgh at the top. Okay? That's the potential energy at the top. That's all your mechanical energy there. The kinetic energy at the bottom is all your mechanical energy there because your potential is 0. So here we have these equal to each other. And what I'm going to do is, like I've done before, multiply both sides of the equation. We're going to solve for v. Multiply by 2, top and, both sides. Then I'm going to divide by m, and guess what? The m's go out. It doesn't matter the mass of these things. The formula is going to be the same. The v at the bottom squared is going to be 2gh at the top. And then to get the actual speed, take a square root. So v at the bottom is going to be the square root of 2gh at the top. And that's the formula they give you at the bottom of the page. They don't specify here, but that v is velocity at the bottom and h is the height above the reference level at the top. Okay? So I just thought it made more sense to put that in here. See, they don't show the second. Oh, yeah, there's the second part of the picture. That's when it hits at the bottom. See, you release it, just let it go, and it goes driving down. So there, right before it hits, all your energy is kinetic energy. That's where it's at the max. And your potential energy is 0 because you measured your h from that top of the pile. Okay. All right. I don't think we have time for example 1. No, we don't. Get my pencil out. We will pick up next time with example 1 on page 220. Okay. Let's see how far we've got. Oh, hey, we are almost through with chapter 8. Okay, so I will try to have your test ready for you next time, which means I kind of like to have your first test in by next time. Not that it matters that much, but it just gives you an idea how you're doing. Huh? If you got it now, I'll take it now, for sure. Okay. All right, good to go. Thank you. Okay. What's that? Oh, okay. No, oh, there's a staple. I don't know if it's got staples in it. We sure can use it. All right. You want to have that here ready? What's that? Oh, okay. Oh, wow. Getting them all in. People out here. All right. Good deal. Oh, I forgot to tell you, sort of a good news, bad news situation. The good news is next week is spring break week. The bad news is we won't see each other. Get over it. Okay, so again.
We'll come next week.
What's that?
We'll come next week.
Mini
No, you
turkeys
don't. Oh, y'all didn't know that?
No.
What's that?
Can you put the test on blackboard?
Can I put it in the test?
Yeah,
Or
look for it.
oh, you scores?
No, the, chapter 8.
Oh. Let's see. Yes, I probably can. I think that y'all read word files better than you do. Wait. I get it off the test bank and it comes as a TST file. What I'll do is I'll ask the secretary to load it to PDF and put the PDF out there. So I can read those down. Okay, good deal. And I think I'll go and turn this off. What's that? It should have.
think they would have a remote.
But I'm tall enough I can reach it. I don't like using remotes if I can reach it with my hand. And then I got able-bodied assistant here, okay? Back over with that so it won't walk away or something. You know. Oh, yeah.